In this first video for 5.1, we're going to have a short introduction to polynomials, how we classify them, where polynomials kind of come about. And this is the first little problem from the section in the book where we're given a sequence of numbers, -4, -6, 4, 50, 156, and 346. And if this was a linear model, then these first set of differences would be the same. Well, obviously they are not. And if we continue finding those first differences, now we took -6 minus -4 to get the -2, 4 minus -6 to get 10, 50 minus 4 to get 46, 156 minus 50 is 106. And then 346 minus 156 is 190. Now, the first set of differences aren't the same. If we find the second set of differences, we have 10 minus -2. That's how we get the 12. 46 minus 10 is 36. 106 minus 46 is 60, and 190 minus 106 is 84. And finally, finding the third set of differences, 36 minus 12 is 24. 60 minus 36 is also 24. And 84 minus 60 is 24 once again. So we find in that third set of differences, there are constant differences of 24, which means if we go back to the second set of differences, this next difference, once again, the difference would be 24, so we would take that 84 and add 24 to it, we get 108. Which means the difference between the next term and the first set of differences in 190 is 108. So that next difference, or this next first difference, if we take 190 plus 108, we get 298. And that means we would add 298 to the 346 to get this 8th number in that sequence. So adding 298 to 346, we would end up with, that's 2 short of 300 to that, so that would be 644 would be the next term in the sequence. And where this kind of stems from, and we'll talk about this in a later video today, that wherever we find the constant differences, that is the polynomial model, or the degree of the polynomial model that describes that data. Now, the first set of examples is just a little bit of an introduction into polynomials. And polynomials and polynomial functions look like this. It might help to look down here at that specific example of a polynomial function, and this is a cubic function because of the degree. And in standard form, we always start with the largest degree or exponent on the variable first, and then work our way down in order. And that is standard form. So we're going to look at some specific examples where we rewrite polynomials in standard form and also classify them according to their degree and how many terms they have. Okay. Now the three big words you need to remember as far as number of terms is monomial, binomial, and trinomial. And it's good to know what those prefixes mean. The prefix mono means 1. The prefix bi means 2, and the prefix tri means 3. So a monomial will have 1 term, a binomial 2 terms, and a trinomial 3 terms. We don't use special words for polynomials with more terms than that. Then we tend to say it's a polynomial of 4 terms or 5 terms or how many ever we have. Now, as far as degree goes by the largest exponent on the variable you see. Constants have a degree of 0 because there is no variable. Linear polynomials have a degree of 1 because the largest exponent on the variable is 1. Here the largest exponent is 2, so that's second degree. We've talked about those for about a month now, and those are quadratics. And third degree polynomials are cubics. Fourth degree polynomials are quartics, and fifth degree polynomials are quintics. So on the next page, in the last little bit of this video we're going to do, is we're going to classify polynomials according to their degree and how many terms they have. So, I went one too far. There we go. In this first example, we're going to write each one in standard form. So writing these in standard form first, we're going to start with the highest exponent and work our way down. So in A, our highest exponent is that x squared term. So we're going to have 9x squared. Next highest exponent is the 1. So plus 3x plus 5. And that is our polynomial in standard form, starting with the highest exponent first and working our way down. Now, since that highest exponent is 2, second degree polynomial is called a quadratic. So this one is a quadratic, and then we go by how many terms we have. And we have 1, 2, 3 terms, so that is a trinomial. So we call this particular one a quadratic trinomial. Quadratic because it's second degree, trinomial because there are 3 terms. Now in this next one, we have some like terms that we need to combine. Again, we're going to look for the largest exponent first. In this case, it's the 4. So we're going to have x to the 4th. And then our next largest exponent is 2. And we've got a couple of terms with that, so we're going to combine those. And we have negative 6x squared plus 10x squared, which is 4x squared. And then our next highest exponent is 1. And then finally, our constant term, minus 12. And so in this case, our highest exponent is 4, so this is a 4th degree. And we call 4th degree quartics. So this is a quartic. And since we have 4 terms, we really don't have a special name for a polynomial with 4 terms. So we'll just call it a quartic polynomial with 4 terms, or perhaps a 4-termed quartic. So that is classifying these polynomials. In the next one, Again, writing in standard form, our largest exponent is 4, so we're going to write that term first, 5x to the 4th. And then the next highest exponent is 3, so 3x cubed minus x. Now it is in standard form. We work our way down in order of exponents. And now we're ready to classify it. Since our highest degree is 4, once again, it is a quartic. And since we have 3 terms, we call it a quartic trinomial. And lastly, D. Again, writing it in standard form, we're going to start with the 5th degree term, the negative 4x to the 5th. Again, very important, keep signs with those terms. Since the 4x to the 5th was negative to begin with, we're going to keep it negative. And plus 2x squared. And we've got a couple of constants to combine, the 3 plus the 10 to have plus 13. And the degree of this polynomial is 5. It's the largest exponent. So we call it a quintic. And since we have 3 terms, that is a trinomial. And we call that a quintic trinomial. And that is classifying polynomials. In the next one, we're going to look at end behavior of these polynomials.